Hello everyone, I will present today TASHAROK using mechanism design for enhancing security resource allocation in interdependent systems. This is Mustafa Abdallah from ECE at Purdue University, and that's based on the joint work with my colleagues and advisors from 4 different institutions. So the agenda for today will be as follows. I will start with the motivation for our work and then the interdependent system setup and the mechanism design, our evaluation, and I will then conclude the talk. There are too many challenges in today's systems security. The first one is the security issues because everything is now connected to the internet. There is a huge increase in cyber threats. And the second issue is the high costs because the cost of high cost of the successful attack. So for example, here I'm showing from the Center for Strategic and International Studies that there is exponential growth in the number of cyber attack incidents with 1 million plus reported losses in the last decade on institutions and governments. And actually, we explore in particular the human decision-making in security. The existence of human in decision-making in security has been revealed and was explored in several works, but actually most of the literature considered optimal decision-making, such as these seminal works and surveys that focus that human decision maker is rational and has optimal decision-making strategy. However, behavioral economics show that humans are only partly rational and deviate from such classical models. Prospect theory, for example, showed that actually human would deviate from such classical models. In particular, prospect theory showed that human perceptions of losses and probabilities would be different from the true values, which would lead to a significant impact on the security investments made by the stakeholders or defenders. In particular, it has been shown that humans overweight low risk and underweight high risk. As shown here, there are a huge amount of the literature that proved such behavior empirical. Here I'm showing 2 seminal papers of Prelak and Gonzalez that has this mathematical form where alpha controls the extent of overweighting and underweighting. If alpha equals to 1, actually here we have a rational decision maker, but if alpha is less than 1, we have a behavioral decision maker that overweight and underweight probabilities depending on the range. Now I provide the interdependent system setup. So we consider a directed acyclic graph, which is a general graph J with a set of nodes V and set of edges E, and each node represents an asset in the system, and the attacker can start her attack from a source node A, and we have multiple defenders. Each defender is responsible for a subset of the assets. For example, here defender D2 is responsible for defending these green nodes. And when an asset VI is compromised, it can be used by the attacker to attack another asset VJ if there is a connection or edge between these 2 nodes. And this attack on that edge VI VJ has a probability of success, which is we denote by PIJ. And we consider LI as the financial loss that the defender would have if her asset VI is compromised by that. Under such attack, we consider defense strategies where we consider that the defender can allocate resources on the edges to reduce the attack probability or risk, where XIJK is the defense allocation by defender DK on the edge VI VJ, and we assume that multiple defenders can assign defense resources on the same edge for joint defense. Therefore, the successful attack probability would be ideally a decreasing function in the total investment Xij on that edge. And also we capture the real world scenario that each defender does not have infinite budget, but each one has a limited security budget PK, where the summation of all of my security investments are upper bounded by this PK. Before going to formulation of the true cost of our problem, actually, I would like to emphasize that each asset here can be attacked using several ways or several paths. So here, for example, the node VJ can be attacked using this path with 2 edges or this path with 3 edges. And therefore, the attack probability on a path, for example, this red colored path, would be the product of the probabilities of successful attack on all of the edges on that path. And to assume that the attacker is a worst case scenario or chooses the most vulnerable path from the source node A to the asset. And actually, this general or worst case scenario can be used to model unknown attacker strategies. Therefore, the cost of the defender will be given by this formulation, which is for each path, we have a probability of successful attack, and we aim to minimize the maximum path along all of the possible paths to the SVM. If the attack succeeded, we will have a loss LM, but remember that we don't have a single loss, but each defender has several assets, and therefore we do summation over all of the losses of all of these assets. But we as humans are not rational decision makers, but we are behavioral decision makers. And therefore, here we consider such behavioral bias or misperception from prospect theory, where the perceived cost is pretty similar to the true cost, but with the fact that the defender would perceive the risk or probability of successful attack on each edge in the attack graph. Under such setup, we seek to answer two main research questions. First one is, how does misperception would lead to or affect the optimal security investments? And second, how can we incentivize stakeholders and encourage them for better security decision making? To answer the first question, actually, we explored the impact of the behavioral bias on investments. And as shown here, actually, behavioral bias would lead to suboptimal investments, which would increase the loss. So actually, in our previous work on HSCCS last year, we showed that risk misperception would lead to suboptimal security investments, and these suboptimal security investments would lead to much higher security loss. For example, here, for this simple setup, we have 2x increase in the expected security loss. I'm just asking you to imagine how would be the fold increase and the huge increase in the expected loss and the system loss if we have real world assets that actually worth millions if compromised. But actually, the need of the mechanism design is twofold. The first reason that I just have mentioned, the effect of behavioral bias, that since behavioral defenders invest in a suboptimal manner. And the second is that even if the defenders are rational, they actually will invest in a selfish manner. Each one will only care about defending her subnetwork. Therefore, we need central agency investments or that would lead ideally to social optimal, which is surely better because it would lead to social cost, as we proved in the paper, compared to selfish investments. So the research questions we need to answer: can we design a mechanism that help the defenders or incentivize the defenders to invest in a better manner to protect their systems and the whole systems and make it more secure? And actually, the idea here is for the central authority to guide the behavioral defenders, and we build on text-based mechanisms and adapt it for security of interdependent systems. Simply, our setup is that the cost of each defender is the original cost plus a tax, and this tax, or term TK, is the security tax which is collected by the central agency. And we adapted two mechanisms, the externality and VCG. And also, as I will explain later, for these two mechanisms and the effect of bias on security tax amount, we explore that as well. And actually, one other motivation for our proposal that cyber insurance is a very promising direction. So because the government can make participation in cyber insurance a prerequisite for the companies to receive security funding and help them in their business opportunities. And there are several proposals in that direction. For example, the California proposal for mandatory cyber insurance in that. And this central mechanism has several properties, but we are focusing on one main property, which is weak budget balance property. Recall that TI is the security tax paid by the stakeholder or defender DI, and N is the total number of the defenders in the network. So we aim for WBB, or weak budget balance, which is the summation of all of the taxes paid by all defenders should be non-negative, because if that doesn't hold, we will have a budget deficit case in which actually the mechanism would require the mechanism designer or the central agency to go and take money from her pocket and use and spend it, which is actually external resources, which is not deserved and doesn't make sense. So now I will focus my attention on the externality mechanism and how we adapt it to our problem. So actually, the idea here of the externality mechanism that for each edge, if one defender invests on my edge, my cost will be affected by that. So the taxes would be depending on such externality, which is how much my cost as defender DK decreased or increased depending on that investments. And therefore, the total tax would be simply like summation over all of the externalities by all defenders on my network. So the simple intuition for such externality mechanism that each defender will pay a tax amount, and this tax amount is proportional to how much I gain or what is the positive externality that I will gain or my cost will decrease depending on other defenders' investments on my edges, which is my network. Also, we explore the effect of behavioral bias on taxes. We prove that under the externality mechanism, the amount of taxes actually paid by the defender is a decreasing function in her behavioral level alpha T. In other words, the behavioral defender will pay more taxes compared to a rational defender. The intuition for that the behavioral defender will see a different drop or higher drop in her perceived loss or cost due to it from other defenders, which would encourage him or her to pay more taxes. The second and the more popular one we adapted is the VCG mechanism. Actually, the idea of VCG mechanism depending on how I benefit the society. So here, if X star minus K is the equilibrium by all defenders excluding DK, and X bar is the equilibrium by all defenders including DK, the tax would be simply the social cost of others excluding me minus the social cost of others excluding me, but this one with my investments and this one without my investments. So just to go like simpler without any math like complexity, the idea is that if the defender DK's investments make my system worse, then the tax amount would be positive. In other words, the mechanism would have a penalty of the defender because you made the society more or less secure with more cost. But on the other hand, if the defender investments make the system better or make the system with less social cost, the taxes would be negative. And therefore, actually, the tax will reward you and the defender will receive a reward for enhancing our society by reducing the social cost. So based on such setup and two mechanisms we adapted for our problem and the properties we prove, now we go to the evaluation. Our evaluation tried to answer these questions. First, what's the gain of using mechanism design for helping behavioral defenders to achieve social optimal? And second, how does the level of behavioral bias affect the outcomes of our mechanism design? So to answer these two questions, we evaluate our approach using 4 attack graphs based on real-world attack scenarios. And actually, these scenarios were built using like well-defined standards such as the NIST guidelines and NESCO guidelines. First, we show the superiority of social optimal over selfish investments or BNE. As shown here, the social cost under social optimal solution or defense or mechanism design or social defense is actually much lower compared to the social cost under selfish investment, especially with behavioral defenders, because each one will be selfish and also waste his resources. One other thing we observe that the difference actually between these social costs is higher. As you see here, these social costs is much higher compared to the social optimal, especially with systems with high degree of interdependency, such as the SCADA system. Next, we show the amount of taxes for each mechanism. So to begin with the VCG mechanism, each player will receive a payment or pay negative taxes because he will help and contribute to enhancing the society cost. On the other hand, the externality mechanism, each defender will benefit and therefore each defender will pay positive investments or payments. However, in both of these scenarios, actually we show in our evaluation that the amount of taxes increases as the defenders has more bias or become more behavioral. Finally, we also show the superiority of TASHAROK over baselines. So we compare our approach to TASHAROK with 4 baseline approaches under rational decision making, and we calculate the social cost under each baseline defense allocation. As shown here, we have 4 systems: distributed energy resource failure scenario, SCADA control system, e-commerce, and voice over IP. And as shown here, our approach to TASHAROK has superiority or lowest social cost compared to all of these seminal baselines. Just to conclude my talk, we first adapted 2 text-based mechanisms for our general framework. This framework involved attack graph models that model large-scale interdependent systems that have multiple defenders. And each human defender in these interdependent systems misperceive the risk on each edge in the attack graph. And also, we proved the impossibility result that there's no guarantee of weak budget balance in our interdependent security game, but more details can be found in the paper. And finally, we characterize the impact of such misperceptions on tax payments made by each defender. We believe that our work will help to build better mechanisms and build better and implement better security policies that can be applied to enhance the 2 issues I have mentioned in the beginning of my talk. Thank you, and I'm happy to have any questions.
Okay, so perfect. The author is on Zoom. So if there is any question from the audience, feel free to step out in front. No? Let me see if we have questions. No questions. So I will ask one of mine. I was with, if I thank you for this very intriguing topic. I was wondering if you can give more insight of this cyber insurance that you were mentioning, because I understand the concept of taxes and everything, but how would it entail, like you mentioned in California, so I was surprised, how would it work in practice, in real life?
Yes, thanks for the question. So actually the idea of having our idea implemented in cyber insurance in general is like to have generally instead of the taxes being just collected based on like the social cost or the behavior which leads to the security investments, it will just be something bit upfront. So I will in the beginning the company or the central company or central agency will collect some like pro amounts, and based on that I will transfer my risk to her. So when, for example, if my system is compromised as like a stakeholder or as like a sub company or even a company, the central agency or the government agency will pay such like part of all of these security losses to me. But actually in our current setup in the paper, we don't consider cyber insurance. We consider that we will try to collaborate and each one make better security policies. And based on such policies, we will pay taxes or receive rewards from the central regulator based on our behavior, or in other words, our security investments or security policies. So that's the difference between just collecting taxation based on the behavior or the cyber insurance, which is mainly similar to the idea of the insurance, but the agency will take the money upfront, and based on that, like if my system is compromised, she will like hold or pay some of the amount or all of the security losses that I will have. So like these 2 ideas, I think both of them are applicable. As I mentioned, there are several proposals and even several initial solutions for that cyber insurance idea. But so I think that would be like a very interesting like extension to our current work.
Thank you. So we have another question.
Yeah, so I was wondering how exactly the graph was constructed. Like, it seems like different companies have, or defenders have different ideas of what their personal cost of not getting attacked is, and what the attack probabilities of successful attacks are. So how do you like build the graph?
Yes, thanks for the question. So actually the idea for the attack graph generation, we tried to see what are all of the possible, like what's the possible attack scenarios based on each like failure scenario. So we had like four like practical systems, which are the distributed energy resource failure scenario, the SCADA control system, the e-commerce and voice over IP. For each one, we start with some like well-known failure scenarios, and based on these failure scenarios, we will come up with some like attack graph or graph that represents such attack scenarios. And for the probability estimation or the probability of attack, default probability of attack estimation or the vulnerability estimation, we followed actually the CVE, the Common Vulnerability Exposure database. So based on that, each edge should represent an attack. We tried to like come up based on this attack and several factors in this like CVE database. You can come up with some like estimation what would be the probability of the initial probability of attack without any defense. So based on that, we tried to like estimate the initial probabilities of attack for each edge.
Thank you.
But surely that estimation may not be like it may not be the I mean exactly the same as the probability of attack, but that's one idea. We tried to like map the real world like databases, vulnerabilities database, to use it to like come up with the initial probabilities.
Yeah, thank you.
You're welcome.
One last question. Okay, we have one last question. Go ahead.
Hi, yeah, that was a very interesting presentation. I was wondering if you consider this also low probability events with catastrophic failures. You were mentioning that SCADA systems are very interdependent, but I think another difference is that they have these basically rare events, the black swan events that are like occur. Maybe they might not occur in our lifetime. Maybe they will. Maybe there's only one. It's like earthquakes, right? Only one thing, and then, well, how do you handle those cases?
Yes, thanks for that. So actually, all of that should like be reflected in the initial probability of attack estimation, or even regenerating maybe the attack graph. But actually, like for our current work, we don't have like variable probability or estimation of the probabilities, but we try to in our model incorporate something called sensitivity. So this sensitivity tries to also shows how the defense can how the security of this edge or the security of our like nodes can be changed according to like our risk. So for example, if an edge that has a very rare attack probability will have two things. The first one is that the probability of the initial probability of attack we estimate would be very low. And the second one, or the second thing we incorporated in our model, that the sensitivity of this edge will also be like will be very high, because like if this is like almost very secure, we don't have to like add more resources on that edge upfront. So, but generally, I think that the estimation will be generally based on this initial probability of successful attack, because as I mentioned in the beginning of the talk, how our bias can affect that, because I think that maybe also more extensions or more trying to explore more what is exactly the difference between the low probability risk and the high probability risk, because according to prospect theory, like generally we as humans, we overweight rare risks, which is overweight low probabilities, and underweight like high probabilities. So we try to focus more in this paper on the high attack probabilities, or the higher risks, but also I think our framework can handle such other cases, but maybe more detailed like analysis for seeing what would be, does it worth it like to spend more resources on that, or how much budget should be allocated to such edges, like more detailed like explanations. I think that would be very interesting extension to our work.
Thank you very much for answering those questions.
Thanks.
And that concludes the. But we can thank again the author for his presentation.
Thank you.